we will start on time because there is much to do, and we have the poster competition in the coffee break. So. Oh, I'm saying this to YouTube. I see. Anyway. I wonder which is this Mysterio 84541. I don't know. There is somebody who is always participating under a number. And I don't know who that is. We will look, but.
Okay, the lane is 3 sharp. Do you want me to start?
Yeah.
Do you want to wait a couple of minutes more?
There is no waiting here. You want to wait 20 seconds so that the 3 is really round because people are piling up now. But let's see. No.
Okay, we reach 60 and I start.
Perfect. Maxim Prosper up there. Olga, fine. Yours.
Hello, hi.
Hi.
Let me turn on my camera. Yeah. Oh, I still have the black hole there. Oh, sorry.
Okay, we are 61.
Okay,
so,
go ahead.
Okay, people, welcome to the last day of the Invisibles meeting. We are very happy to have our first speaker today, John Beacom. We'll try to convince us there is a future on solar neutrino physics. And please, for the speaker not to be isolated, if you can switch on your cameras, but switch off your microphone, it would be great. John, whenever you want, the mic is yours.
Okay, does that work?
Yes, it is.
Okay. Buenos dias a todos. Thank you for the invitation. I'm excited to be here. I wish I was in actual Spain instead of virtual Spain, but this is still pretty nice. So the question today is, do solar neutrinos have a future? Is it dark and stormy or is it bright and shiny? Now, if we answer this question like a particle, we talk about sort of 3 eras in understanding neutrino mixing. The original gangster epoch, we had the solar neutrino problem and we eventually solved it. In the golden epoch by measurements with snow and camland that decisively showed that solar neutrinos mix, they mix to active flavors and to measure the sine squared and delta M squared. And in the coming golden epoch with all of the long baseline experiments and reactor experiments, we're going to measure basically everything there is to know about 3-flavor neutrino mixing. And you notice those future experiments are primarily, well, they're laboratory experiments, reactor and long baseline experiments. So that leads me to my conclusions that there is no future. We've decided that the choice is Dune and Juno and other things like that, and we don't need solar neutrinos anymore. So, okay, thank you. I'm glad I could finish on time. And that's really the whole story. Oh, okay, maybe there's more. So that's the particle physics view, in a sense that really we don't need solar neutrinos anymore. But I'm really also an astrophysicist. So as the astrophysics point of view would say that the real reason we study solar neutrinos is to look deep into the interior of a star. And this is a dream that's more than 50 years old. This doesn't say anything about measuring particle properties of neutrinos. It was prescient, but not that prescient. But really, this is not the correct view either. The correct view is really kind of both. And the first idea is that we can use the extremes of astrophysics. It's kind of like a long lever arm to probe particle physics that we can never probe in the laboratory. And we can also use our knowledge of astrophysics. We can also use our knowledge of neutrinos to probe extremes of astrophysics that we can't probe any other way, for example, with optical astronomy. So it's the combination of these two things that makes solar neutrinos and other kinds of astrophysical neutrinos so interesting. We have to understand the sources, and we have to understand the messengers, and we have to do them with the same set of data. And that's challenging. It's an opportunity to do both, but it's challenging because how do you learn the source if you don't know the messenger, and vice versa? But there's a way to do it together. And in solar neutrinos in particular, I want to emphasize an important point. There are a lot of people in the field who think that solar neutrinos is over because there's not really anything more to ask. The questions have been answered. And that's really a wrong point of view. We did not run out of good questions in solar neutrinos. We just ran out of experiments. And so this talk is about finding better experiments. And I'll highlight the questions that remain open. So on the particle physics side, this is a plot of the survival probability versus energy. And one of the things we would like to do is measure the energy dependence of the MSW effect. And I want to highlight something here. We have never measured this. I mean, we make this curve all of the time, and we show it and we're used to it, but we've never measured it. So what we've measured is at low energies, the survival probability is high, like 2/3. At high energies, the survival probability is low, it's like 1/3. And in between, we have never seen what happens. There's a little bit of data in between, but it's not enough to really see MSW versus other possibilities. So the most fundamental thing in MSW physics has never been measured. And this also opens up the opportunity to look for new particle physics. But in order to get the most out of this particle physics, we have to understand the astrophysics, that's the sun. On the astrophysics side, we've measured, pretty much all of these fluxes to some degree, but there's still things to be done. We've still never isolated the HEP flux at the highest energies. The CNO flux has been kind of tasted, but not well measured yet. And we still don't understand the metallicity of the sun. And in order to solve these astrophysical problems, we have to understand the messengers, the neutrinos, better. So how are we going to do this, solve these two problems at the same time? Well, we need obviously a new generation of experiments. And the job of theorists is not only to wait for experiments to happen, but to help motivate them to happen. So the two challenging experimental problems are to measure the low energy solar neutrinos where the fluxes are high, and you need detectors really only at the ton or kiloton scale, but it's very hard to improve on things like borax, so we have to be much bigger and better. And separately to measure the high energy fluxes, boron 8 and HEP, where the fluxes are very low and we need huge detectors at the 10 kiloton scale. And there it's very hard to improve on super K and snow, but we have to find a way. So one possibility is using liquid argon, and there's a bunch of things about liquid argon that are special. And this has been talked about for a long time. I mentioned some of the references here, going back decades. So let's see why this could be so special. So what's good about liquid argon is it images particle interactions in 3D. That's the fundamental thing. And that allows you to better measure particle directions, energies, which reaction happened, and to better separate from backgrounds. This is a picture of higher energy interactions, but it gives a similar idea. So at low energies in liquid argon, people have been talking about large detectors that could measure solar neutrinos, and here's an example. This detector doesn't exist yet, but it could. And a detector like this would be able to measure the low energy fluxes rather well. And in this paper, they talk about the measurements, but they don't talk about the prospects for measuring new physics or even really the oscillation physics. They just say this could be measured. So I think there's a lot more development that could be done. And liquid argon is not the only way. People are talking also about liquid xenon and other technologies. And new ideas are needed. I'm focused today on the high energies, which is Dune. So Dune offers an opportunity that it's the next multi-10 kiloton detector, comparable in size to Super K, and if it could measure solar neutrinos well, that could maybe be a breakthrough. So we've studied this in a couple of papers. It's really, looks like 2 papers, but it's really 3 because the supplemental material from the first paper is itself gigantic. And the reason all of this took a lot of time and details is because there are a lot of technical challenges. We think those technical challenges are surmountable. And that's a new idea because in all of the Dune documentation, solar neutrinos received only glancing mentions because it was thought to be too hard. We think it's not too hard. So the whole Dune. Dune is the next gigantic detector and has 3 main goals. Notice that solar neutrinos is not one of them. They have 3 very beautiful icons that I don't know if you could understand those unless you put the words. But, and even if you put the words at the top, origin of matter, unification of forces, and black hole formation, it's not totally obvious what they mean. So I put underneath what it actually means. And, one of the goals of Dune is to measure MeV neutrinos. So they have to have some MeV capabilities, but I want you to notice that the proton decay and the long baseline stuff does not really care too much about the low energy capabilities. Now, they should, because as Shirley Lee and others have shown, measuring the low energy particles is part of reconstructing what happens at a GeV. But there are a lot of people in Dune who frankly do not care about the detection capabilities below 100 MeV, and they should. So part of our motivation in making this case for solar neutrinos is to help improve Dune as an MeV detector, which will help its ability to detect supernova neutrinos. We've highlighted some issues that need further attention from the collaboration. So, okay, what is Dune? Now, there's a spherical cow, and there's basically spherical Dune is a giant bucket, 4 buckets, each has 10 kiloton of argon, and can talk about the details, but we made a series of reasonable conservative assumptions about how the detector would work. The part that makes some of the experimentalists edgy is we assume that the detector works pretty well down to about 5 MeV. And we also assume that the energy resolution could be relatively good. It may be challenging to do both of these. It turns out you don't need both, you need one of those. And also, since the time of our paper, the experimentalists have made a lot of progress on the prospects for reaching these goals. The angular resolution requirements are rather modest. So the goal is energy resolution is important. Energy threshold is important. Angular resolution is probably safe. Okay. So what the goals of our paper and everything else here? What we want to do is in particle physics, our goal would be to make the world's best measurement of sine squared and the world's best measurement of delta m squared, and to make powerful tests of new physics. In other words, we think the goal is to make Dune the world's best solar neutrino detector. And on the astrophysics side, the goal is to make the world's best measurement of boronate flux and the first discovery of the HEP flux. And by combining with other data, to make powerful new tests of solar astrophysics. These are really ambitious goals, and I'm not yet saying that we reach them. I'm saying this is what we want. And if we do reach these, it would be amazing. And that would be not we the world makes these goals, it would be amazing. And it's hard. And you have to break the degeneracies between the particle physics and astrophysics. And it's extremely challenging. But if this were successful, it would really, really matter. Now, let's see if it can be successful. So the Dune or any liquid argon detector has two key charge current detection reactions available to it. Let me be more precise. The first one there on the nucleus, nu E plus argon, is a charge current only reaction. And it makes an electron, which we'll measure, and it makes an excited potassium. Now that potassium will decay by gamma ray emission, and we very conservatively assume that those gamma rays are not detectable. if they are detectable, everything I say following gets incredibly better. So let's do the conservative thing and we'll just count the electrons. The second reaction is, of course, a mix between charge and neutral current. That's electron scattering. There's a third reaction, neutrino plus argon neutral current. And unfortunately, the cross-section uncertainties for that are huge. Some papers think it could be very appreciable, and other papers think it's tiny. If that reaction were available, it would make everything I say even better. So we conservatively neglect it. So the goal is, like with snow, you remember with snow, they measured a neutral current reaction and a charge current reaction. And by comparing the two, they could figure out what was going on with the mixing. And that's basically the same idea here. So you have on the x-axis the nu E flux, and on the y-axis the nu and tau flux. And you remember what snow did is they measured the neutral current flux, which is a diagonal because it's the sum of the two flavors, all flavors. And they measured the vertical, which is the nu E only. And then they looked where they crossed and they said, aha, that tells us the true values. And from that, you can extract some mixing parameters, design squared. So here, what we want to do is we want to measure the charge current, it's vertical, and we want to measure the electron scattering, which is barely not vertical. So it's incredibly hard compared to snow to get the difference between the vertical line and the barely tilted line. But Dune would have the statistics to isolate those two lines that have a very small slope between them. So that's how you could measure the mixing angle without having to make assumptions about the astrophysics. This is a self-calibrating experiment. You have two measurements in the same experiment that enable you to separate the flux and the mixing angle. Then, in order to get the delta M squared, we have to use the day-night effect. This is also super hard. Super K has a few sigma hint, but nobody has a great measurement. And the thing about Dune is that few advantages, among them giant statistics. Another is the cross-section rises more sharply with energy, and the day-night effect goes up with energy, etc. And so Dune could also make a superb measurement of the day-night effect and measure the delta M squared, independent of astrophysics, because again, it's two measurements in the same detector, day and night, just compare them. So this is how these degeneracies could be broken. And this spectrum here shows what things could look like. So we define on the right side, inside a forward cone, that's where the electron scattering events are, mostly, and outside a forward cone, which is where everything is. And I call your attention to the x-axis, where the only thing we count is the electron kinetic energy. We don't count the gamma rays. If we did count, if you see an event with gamma rays, then you know that it's a nuclear event and you can separate it from the electron scattering events. We don't assume that. So the only separations here are statistical. So again, if you can tag the gamma rays, you can separate the events nearly event by event, and then the blue versus the red could be easily separated. And that just makes everything even better. So you would, with the gamma rays, you would get better event separation and better energy measurement, which only helps. This is the worst case. Okay, so this is basically the goals. What are the obstacles? Sorry, here's another part about the goals. So on the left-hand side, we show the present situation where the reactor delta M squared is measured beautifully. And on the right, we show how the reactor delta M squared is going to be measured insanely perfectly. And on the left, we show the present solar delta M squared. It's gigantic. And without Dune, it will remain gigantic basically forever. So you will have a chance to compare reactor and solar only if we make a measurement with Dune or some other experiment. So that's why it's so important. Okay, you'd also measure the fluxes extremely well. So why does this matter? So there's significant discovery opportunities in both particle physics and astrophysics. It seems like this is possible with relatively modest investments on helping an existing detector as opposed to starting from scratch. We think that no other detector is capable of meeting all of these goals simultaneously. Of course, Hyper-K will have some important measurements. Juno may as well. But there's noted and proposed detectors like Theia might, but there's no detector that can do all of this. And if other detectors can do part of it, it's only better for everybody. So the last point is a little bit depressing, and nobody ever says it, so I want to say it sharply. If we don't do this with DUNE, this is our last chance to measure solar neutrinos. There is not going to be a bigger, better detector after the present generation of DUNE, Juno, Hyper-K. There's just not going to be a bigger detector, I think. You can't count on that because once the golden era and you've measured all the neutrino mixing with long baseline, who's going to build a giant detector? They did not build that detectors for solar neutrinos. They did not build them for supernova neutrinos. They built them for long baseline and reactor. And when those goals are met, that may be the end of it. So if we want to be part of this story, we have to do it now. There are a lot of obstacles. One is the cross-section. It's not as well known as it needs to be. We discuss in great detail that the present uncertainties are about 10%, and feasibly these could be pushed to 1%. It also cancels in the day-night, although not in the flux measurement. There's the possibility of tagging the gamma rays, which I talked about a little bit. That would be wonderfully important for tagging the events, separating from backgrounds, and better measuring energies and things like that. And another obstacle is the detector backgrounds, and we've calculated these in detail. This is one of the things that worried people quite a bit at the beginning, but we have these giant studies where we go into all the details on the backgrounds. They're all manageable. One interesting one, people talk about trying to measure the DSNB with DUNE, but the killer is solar neutrinos. Solar neutrinos basically make it impossible below, something like 15 or more MeV, 15 or 20 MeV. Okay, so what's going on in DUNE now? Here's some important work by the experimentalists that I want to highlight. This is not all of it, it's just some of it. So the Duke group has been working on making reconstructions, and they think that it's very possible to see some of these de-excitation gammas, which I'd mentioned would make things only even better. This figure is a little hard to read, but this big blob that I'm circling now, that was our delta M squared region. Sorry, that's the current region. And this green thing is what DUNE could measure. And then if the truth is down here, it could measure something like that. So basically, with the gamma ray detection, you can squeeze things even more. Now, there's cause also for a little more pessimism. One of the backgrounds that's a concern, people are concerned about, I'm not concerned, but other people are concerned, is radon. And a lot of people are freaking out about radon. And part of the reason is radon emits alphas, and there's a rare reaction where an alpha hits an argon and makes a gamma ray, and that gamma ray is an high energy, so that's quite dangerous and annoying. However, everybody who's making these calculations is assuming radon concentrations that are incredibly high. And if you achieve radon concentrations anything like any previous detector, it would be fine. And people know how to mitigate radon. So I'm optimistic that this will long-term be solved. Then another thing people worry about is the neutrons coming in from outside. And here's a picture of one of the proto-dunes, and notice it kind of looks like a waffle. And ideally, you could shield this detector completely with water or oil or something like that. And we talk in our paper, if you shield this with like 30 centimeters of water or oil, you solve the backgrounds by orders of magnitude. However, experimentalists freaked out about that because, water and electricity, not so good. Oil can be a fire hazard. There's, all kinds of practical, real concerns. But it turns out you don't actually have to cover the whole thing. You can put blocks of material inside of these waffles, and with something like 2/3 of the area covered, you can still get a dramatic reduction in backgrounds. And that's because neutrons go like this. And if you have some plastic or oil, bags of water, whatever, eventually a neutron finds one of those and then it dies. So this all needs further work. So to wrap up for real, with liquid argon and other detectors, I think there's a very bright future in solar neutrinos, both to study particle physics and astrophysics. And I think optimizing these low energy capabilities is obviously beneficial to Dune's ability to measure supernova neutrinos well, and to measure the details of high energy interactions. Because when you have a long baseline interaction with the GeV neutrino, counting up both gamma rays, neutrons, and other low energy particles can help you better do the calorimetry. As I remarked, the lack of activity in solar neutrinos is not a lack of questions, it's just a lack of detectors, and that is a fixable problem. So, solar neutrinos, I think there's a future. Thank you.
Thank you for the very fantastic talk. Are there any questions? Yes, Enrique.
I was clapping, but Sergey has a question.
Hello, do you hear me?
Yes,
Sergey.
Hi, John. Nice talk.
Hey.
Thank you very much. In connection with your talk, I would like to remind you the words of Pauli in the letter, famous letter in which the idea of neutrino was proposed. Only those who wager can win.
Yeah.
Now, coming back to your talk, can you show slide number 20? I have a brief comment.
Sure, no problem. How's that one?
So the left figure, I mean, it's a little bit outdated because with the recent day-night data from Super K, this discrepancy between delta M squared coming from solar neutrino experiments and from Kamland somehow is reduced to one sigma effect. So this is no more there. And lastly, a question. Somehow I didn't understand what is the threshold for chlorine for the liquid argon charge current reaction. I mean, you mentioned 5 MeV. Does that correspond to the nuclear transitions and so on?
Yeah. Okay. Good. First, to answer Sergey's question about the progress on this delta M squared figure that we're seeing here, I want to emphasize that the motivation for this case does not depend upon there being a discrepancy between Super K and Kamland.
No, sure. This I understood. So this is only a comment about this left part.
Yeah. So, you know, if the details change, it doesn't matter. But the physics, I know we agree, is to compare two precise things is a good thing. If they disagree now or don't disagree now, what matters is the future. Okay. So now to answer your question about threshold, there are a variety of different nuclear thresholds in argon. And so we did all of our results for 5 MeV electron energy. So that takes into account the energy sort of wasted on the nuclear transitions and making the gammas, et cetera. And it's not known if 5 MeV is totally realistic. I've heard Dune people say that maybe 6 or even 7 is more realistic. I've heard other ones say that maybe 4 is more realistic. And if we can tag the gamma rays, that helps even more, because then what you measure is basically the total neutrino energy. Does that answer your question, Sergey?
Yeah. So basically, as far as I understand, it's not clear at the moment.
Well, but even in the pessimistic case, you can make a great measurement. So in the paper, we talk about the worst case is you cannot detect the gamma rays. And in the paper, we give results if the threshold is 5, 6, 7, 8 MeV, and you can still get wonderful results. And those results are in the appendix.
Okay. Thanks a lot.
You. Nice to see you.
Any other question? If I don't see any hands, yes, Ivan Esteban, I think you can unmute yourself. Or
it's a very quick question, so thank you very much for the inspiring talk. It's a quick question about the DSMB measurement, the diffuse supernova neutrino background. This was somewhere. Yep.
I'll find it. Keep going.
So I may have missed something, but you mentioned that the solar neutrinos basically kill you, and what I see from that plot is that solar neutrinos kill you at lower energies. So is there any reason why Dune has no hope of measuring anything above 20 MeVs or so? It seems
well, I'm trying to call your attention to the two gray lines, which are the solar neutrino ones. So the blue stuff is spallation backgrounds, which we can cut from this dotted line to the solid line. So we have the technology to reduce the spallation backgrounds a lot. But look, the HEP background here and the boronate background here remain. And it's basically a wall.
But if I am probably missing something, but if the analysis only restricts to electron kinetic energies bigger than 20 MeVs or so, in principle, the background is negligible, right?
Oh, yes. Yeah.
Okay.
But then if you look at the counts, they're extremely small.
Okay, yeah.
Yeah, counts are like 0.1 per 100 kiloton year.
Okay, thank you.
Yep, thank you.
Okay, people, okay, we stop, we move ahead, but please remember that there is a Slack channel. If you happen to have further questions, you can go there. There is a special Slack for long talks, and there is another Slack for short student talks, and you can hopefully put questions in both. Okay, thank you very much, Sean, a lot.
Thanks. Okay, I don't do the Slack, but if anybody wants to send me an email, I'm welcome to.
Don't worry. If someone does the Slack, someone will forward it to you to answer.
Okay.
You won't go away with that. Don't worry.
Okay, thank you.
Welcome. Okay, so the next speaker, we move now to the student forum. The next speaker is Marcus Rasmussen, and he's going to talk about easing the sigma 8 tension with neutrino dark matter interactions. And hopefully, okay, he's now sharing his screen. There you go.
Hello, everyone, and welcome to my talk, Easing the Sigma 8 Tension with Neutrino Dark Matter Interactions. I'm Marcus Musbeck. I'm a PhD student at the University of Sydney, and the work I'm going to talk about today, I've done with my excellent collaborators, and it's available on arXiv and published in JCAP earlier this year. So, we had three main motivations when starting this work. The primary one is that oscillation experiments show strong evidence for non-zero neutrino mass, which has not previously been accounted for in this type of dark matter neutrino interaction studies. So we should fill this hole in the literature. Additionally, it would be great if we could solve one of these outstanding cosmological tensions, either the H0 tension, the sigma 8 tension, or maybe both. So our work has been separated into three main parts. First, we derive the analytical equations, the math needed to describe this interacting scenario, where the new thing we've added is the non-zero neutrino mass. We then implement all these new equations in the Boltzmann solver class, which will let us calculate the CMB power spectrum and matter power spectrum for our interacting models, which we then further interface with the MC code MontyPython, which allows us to obtain constraints for the cosmological parameters and the correlations between different values of the parameters. So I'll talk a little bit about the Boltzmann equation now. What you see here is the general relativistic Boltzmann equation. So it describes the evolution of the distribution function for a given species. And on the left-hand side here, you see the time derivative and the gravity terms, where on the right side here, you see whatever interaction terms are given for a species. So in the early universe, we have a very homogeneous state. So instead of evolving for the full distribution function, we can evolve for the perturbation to the distribution function, greatly simplifying our equations. And additionally, we can then perform a Legendre decomposition and go to Fourier space. So we get a hierarchy of different equations that might depend on each other, but in Fourier space, the different scales decouple, so you can evolve each scale separately, which is very nice when you solve it numerically. Here we see the equations for normal cold dark matter non-interacting, where you see the continuity equation here is the 0th moment, where the evolution of the density contrast only depends on the velocity and the gauge fields, and the Euler equation here, where the evolution of the velocity field only depends on the cosmological expansion of the universe and gauge gravity fields. This is not as simple for the massive neutrinos as they go from being relativistic in the early universe to non-relativistic in the late universe. So we get a full hierarchy that must be truncated at some point, as well as momentum-dependent equations that must be solved separately for each momentum bin. However, we implement our equations with interactions in class, and we get a matter power spectrum that looks sort of like this. We get suppression of power at small scale, similar to warm dark matter, but with these characteristic oscillation peaks. And this matches our expectation from the massless neutrino case done previously, with peaks shifted to slightly smaller scales due to this newly introduced p squared over e squared term that appears as a result of including the neutrino mass. So when we perform our MCMC, we find sadly that we're not solving the H0 tension. However, we see that for a larger interaction parameter U, we have a much lower value for sigma 8. Here, the gray blob is the Planck measurement. The purple-ish blob is the KITS 1000 result, and they're strongly in tension, as you see, which is the sigma 8 tension we talk about. But you see here behind that, in our interacting case, which is performed with Planck data, we have a large overlap with KITS 1000, thus easing the sigma 8 tension. This is just one possible way of doing this. There are other, but the nice thing here is we're not making the H0 tension worse, which is something a lot of these solutions tend to do. Thank you all for listening. I'm happy to answer one question, I think, and otherwise on Slack.
Thank you very much. Again, is there at least one question? I do not see any question, but I'm sure there should be some questions in Slack. So let's move. Jorge Terol is our next speaker. And Jorge is going to talk about supernova constraints on the dark flavor sector. Jorge, whenever you feel ready, go ahead. I cannot hear you, Jorge. I'm not sure whether you are talking or not.
Now I'm muted. Now, can you see the slides? Yeah, everything right.
I see the slides and can hear you.
Okay, yeah. So, well, yeah, it is a real pleasure to present our work in this wonderful workshop. And as you said, I'm going to explain you how to put constraints on dark flavor sectors with supernova. And yeah, usually a dark sector is often thought to be universally coupled to the standard model. However, in principle, you can have models with a flavored dark sector. An example of that is the massless dark photon. And yeah, rotating to the gauge fields to a basis in which there is no coupling, three-level coupling from the dark photon to the standard model. These couplings only are generated with higher order operators, and this arise in UV completion model with flavor structure. Another example of this is the axion. There are models with non-universal Peché-Quinn charges, for example, models that are connected to, they try to solve the flavor puzzle, or even if they have universal Peché-Quinn charges, via radiative standard model corrections, you can generate these flavor puzzles, flavor violating couplings. So now supernova, boom, in 1987, for the first and only time, it was detected a supernova with neutrinos. This neutrino signal gave a lot of information on how the supernova cools. And this tells us that if there is a new cooling mechanism, this neutrino signal would be altered. Thus, there is a bound on the luminosity of this dark cooling mechanism, and it is that it cannot be larger than the neutrino luminosity. Okay, so we propose a strange cooling mechanism. It has nothing to do with Dr. Strange. Of course, it has to do with hyperons, because in the protoneutron star that is produced in the supernova, the conditions are favorable for the lambda hyperons to be produced. So using the latest simulations on this particular supernova and equation of state, including hyperons, we have been able to derive the radial profiles of the abundances of the lambda hyperons and many more quantities, thermodynamical quantities that are useful for our calculations. And now, if we have a dark boson general that couples has this flavor coupling that allows for the lambda to decay, then we have a new dark cooling mechanism. So we have computed how is the cooling rate, that it has a dependence on the decay width of this process. And we have taken in account, of course, the reabsorption and the trapping regime. So with all of this, we have computed the dark luminosity as a function of the branching ratio of this process. And in gray, you have this bound that I have told you about. And taking the most conservative approach, we get a bound on this branching ratio of the order 10 to the minus 9, 10 to the minus 8. So let me stress again that this is model independent, but of course, we can apply it to the models I have talked about. In the case of the action, we get bounds on the scale for this particular coupling of the order of 10 to the 9 GeVs compared to other bounds. In the case of the vector coupling, it is not competitive with the KM physics, but in the case of the axial coupling, gets the strongest bound on this particular coupling and the strongest bound on all of these flavor couplings. And it is orders of magnitude stronger than the current laboratory research. And if we extend this for the ALP case, we get more or less the same results unless we are in a mass region closer to the mass difference of the baryons. Okay, now if we apply this to the dark photon, the dark photon couples through this dipole-like operator to the standard model, and we get a bound on the scale, assuming order 1 couplings are of order 10 to the 10 GeVs. Compared to the other couplings, it says the strongest bound on this particular coupling, because now we don't have, because of angular momentum conservation, we don't have the same decay as the action. So it says the strongest bound on this coupling, and one of the strongest, taking in account other flavors. So I'm done. This is my message that I want you to take home, but it is better explained in this animation. So in the end, astrophysics and flavor physics can be, yeah. Sorry, I got too nervous in the end. So thank you. I'm finished.
Thank you, Jorge. Thank you for the animes too.
Yeah.
I think this audience is not very used to anime, at least. Okay.
No, I think so.
I think we are 20 years past anime. Anyway,
yeah.
Thank you very much. There is one question. Please go ahead.
Yeah.
So you need the number of these hyperons in the beginning. How well is that controlled in the simulations? How well do you know it?
Okay, so let me go back. In the simulations are performed with this particular equation of state. So, well, this one that does not include hyperons, and the LS220 without lambda that does not include hyperons as well. And what we have done is to use an interpolation table of this equation of state, extended equation of state, to get the relevant thermodynamical quantities with hyperons. We know that it is safe because, and the reference by the creator of this database, Compose, Michaela Ertel, and some collaborators have shown that this equation of state get similar results for the relevant thermodynamical quantities in the densities that are relevant for the proton-neutron star. You start seeing difference on the pressure or the temperature, etc., when you get to more than twice the nuclear density, I think. Okay, so in principle, we believe that it is quite safe to use this approach.
Mm-hmm. Thanks.
Thank you very much. We need to move. And if you have further questions, you know, Slack is there. The next speaker today is Mateo Puel. He's gonna talk about Caspi to core galaxy profiles. Okay.
Can you see my slides?
I can see your slide.
Okay, and also can you hear me?
Yes.
Okay, perfect. So hi everyone. Thank you very much for organizing for inviting me. I'm Mateo Puel. I'm a PhD student at McGill University. And today I'm going to talk about my recent work on the possibility to use dark matter oscillations to turn CASP galaxy profiles into code ones. This work is done in collaboration with my supervisor, Jean Klein, and Guglielmo Gambini and Sam McDermott. So the lambda CDM cosmological model works really well at scales larger than a few megaparsecs, but there are some tension on smaller scales between the prediction of cosmological and CDM only simulations and observations of scale of galaxies. One of the most well-known tension is the so-called core-cast problem, which is the tendency of simulations to predict gas speed or metahalos in contrast to observation that prefer more core profiles. The most popular astrophysical explanation is to include baryon feedback in the simulation, which can alleviate the discrepancy. But the most well-known new physics explanation is to make their matter self-interactive. It has been shown that an elastic cross-section, velocity-independent elastic cross-section of the order of 0.1 to 1 centimeter square per gram can do the job, but more likely a velocity-dependent scattering cross-section could be better. Our idea in our paper was to use the meta-annihilations to solve the core-cast problem, because annihilation is an exothermic process like CDM. So we proposed a model with a symmetric dark matter with a small number violating mass term that causes oscillation between particle and antiparticle late times. We considered two classes of models, a coupling between dark matter with a light vector boson V, from which the dark matter freeze out and dark matter late time depletion can be achieved by this annihilation channel. And then we consider the matter coupling with a lighter complex scalar field, from which the dominant annihilation channel is chi into a scalar and pseudoscalar component. For simplicity, we neglected the pseudoscalar dark matter mass, and we considered dark matter Dirac mass around 100 MeV. And also we chose model parameters such that the annihilation processes are dominant compared to scattering processes. Furthermore, both models must contain a Majorana mass term, which has to be very tiny in order to be consistent with SMB constraints and to make annihilation to recouple at the time of structure formation. So let me show some results for the galaxy density profiles that has been obtained with two different complementary methods. The first one was by solving the quantum Boltzmann equation for the density matrix, which are shown with the dot dashed lines. And the second one was obtained by using n-body galactic simulation that show with solid lines. Here I'm showing the density profiles as a function of distance for different choices of the dark fine structure constant for a dark galaxy on the left and a galaxy cluster on the right. With the cyan curve, with the orange curve, I'm showing the best fit for CDM with the velocity-dependent scattering cross-section that is shown for comparison. And as you can see, dark matter annihilation can turn the initial density profiles that are CASP, like the Navarro-Fenton-Webb profile, into core profiles like the CM does. But however, the observables that we can measure is the velocity, is the circular velocity for the dark system and the velocity dispersion along the line of sight for galaxy clusters. The bottom plots have been obtained by translating the results in the dot plots into observable quantities, and also we compare them with observational data that are shown in gray and white. These results must be compared with the vector model that are shown in the top, where the only parameter that is being varied is the vector boson mass. And here the trend is the opposite with respect to the scalar model. If we can say that a value of a prime of 0.1, which is the cyan curve on the bottom, can fit really well the DARF data, but a smaller value of a prime will be needed to fit the DARF data. For the vector model, we need a vector mass around 34 MeV to fit the DARF data, but a larger value would be needed to fit also the cluster. So in summary, you can say that the separation in cluster is more efficient with the vector mediator model, while the suppression in DARF is more efficient in the scalar model. So we propose a model with both mediators, and we put in our paper an example of model parameters that can fit both systems at the same time. So thank you very much, like my poster, and I'm open for questions.
Thank you for your talk. Is there any question? I cannot see any question. Let me check No, I cannot see any question. So probably there are some questions in Slack. So we move ahead. We go to Ana Esteban to talk about abundance of black holes. Ana, whenever you feel ready.
Do you hear me?
Yes, we can.
And you can see the slides too.
Okay.
Okay, thank you. Hello, everyone. My name is Ana Esteban. I'm finishing my PhD here at the Instituto de Astrofísica de Canarias, and I'm going to talk about our recent results about primordial massive black holes. And the title of this talk is Abundance of LIGO Virgo black holes from quasar microlensing. As a brief introduction, quasar microlensing serves as a tool to extract properties of any population of compact objects in the lens galaxy, apart from studying the source object, in this case, a quasar. So as we already know, one of the open questions in science is the nature of the dark matter. And in the last years, some new compact astrophysical objects, like the primordial black holes, gained popularity to be one of the candidates of the dark matter. And one of the reasons is because of the LIGO Virgo gravitational wave release data that show unexpected black hole mergers with some low spin and some unusual masses. So the main motivation of this work can be summarized in this question. Could these primordial massive black holes be hidden within a population of compact objects in the lens galaxy, for example, the stars? So the methodology we follow consists of calculating microlensing flux magnification for two different compact objects, stars of 0.2 solar masses and black holes of around 30 solar masses. And we also considered a smooth matter component for the simulations. We use the inverse polygon mapping algorithm to simulate the maps, which traces back light rays from the image plane to the source plane in order to compute the magnification for each one of the pixels of the map. And we also use the Slurm software just to accelerate the process of creating the maps. And at the end, we want to apply a Bayesian statistical method to obtain the probability density functions coming from the microlensing magnifications. And the procedure is, as you can see from here, from a magnification map, we obtain histograms, which we use to calculate the likelihood comparing these histograms with a set of optical magnitudes from gravitational microlensing observations. So as I don't have enough time to discuss all the results of this work, I wanted to focus on the second part, on our second approach for this study. And if you are interested in the rest of the results, you can take a look at the accompanying poster. For this second approach, we consider different abundances for the stars and for the black holes. And also we consider different systems of convergence and shear parameters, which are the main parameters involved in the macrolensing magnification calculation. So here you can see two different plots. On the left-hand side, we see a two-dimensional probability density function plot of the microlensing magnifications. In the x-axis, we have the abundance of the black holes, and in the y-axis, the abundance of the stars. And from this plot, you can easily see that it peaks at 10% of the stars with zero contribution from the black holes. And this can also be seen in the one-dimensional PDF plot shown in the left-hand side panel. And from this plot, we can also see that the marginalized one-dimensional PDF of the black holes, this is the second subplot here, shows a very small fraction of the total matter in terms of black holes, that is less than 1% of abundance at 68% of confidence for black holes of around 30 solar masses. No? And okay, to end up with the conclusions, they are summarized also in the poster, in the accompanying poster. Since I didn't have time to enumerate all of them here, but I wanted to share to you a last slide talking about the upcoming work. So we have studied the abundances of these primordial massive black holes coming from the LIGO Virgo estimates of masses. And so from the previous results, we can conclude that there is no evidence of a significant presence of these black holes inside the lens galaxies. However, a significant contribution from very small black holes mixed within the stars cannot be discarded yet. So we are currently studying the effect of considering a mixed population of stars and primordial black holes of less than these LIGO-Virgo mass estimates. And so we expect to compare these results with the X-ray band observed magnitudes. So stay tuned for more interesting results. Thank you very much for your attention. If anyone has any question, I will be glad to answer.
Thank you for your talk. York, you can go ahead. Okay, I know you are clapping your hands. I'm sorry. I'm confused clapping the hands with raising your hands. It's very misleading, the system. Okay. Anyway, maybe next Invisibles, we can tell you about these new results you are working now. Any other question? Any question? I cannot see questions, so we move ahead. You still can go to the Slack if you have questions. The last speaker of the student session is Rodrigo Calderon. Rodrigo is going to talk about the negative cosmological constant, and hopefully, Rodrigo, when you are ready.
Yeah, I am ready. Do you see my screen?
We see you and we see your screen and we hear you perfectly.
Okay, perfect, beautiful. So thank you, everyone. My name is Rodrigo, and I will briefly discuss some of the implications of introducing a negative cosmological constant in the dark sector. And so at this stage of the workshop, I don't think I need to convince you why we need to go beyond the Lambda CDM model of cosmology, but it's basically summarized in this figure. We have early and late time measurements of cosmological parameters, such as H0 and sigma 8, and these do not match with each other when we measure from early and late times. So more importantly to me, it's the curious fact that we happen to be living in the de Sitter stage, where the scale factor grows exponentially with time. And this is typically due to dark energy, but it has also happened the same de Sitter stage during the early universe, an epoch known as inflation. And so it seems that it's extremely difficult or challenging to construct a stable de Sitter vacuum from a high energy or more fundamental theory like string theory. And so the question we want to ask is, can it be that the dark energy density is composed instead of a negative cosmological constant, which is highly motivated by high energy physics and naturally arises due to symmetry consideration, plus some time of X component time evolving, which will be responsible for the late time accelerated expansion. And so the question is, are such models viable? And if so, how does it affect the measure of H0? So let me briefly remind you how we infer the value of H0 in the cosmological constant. So we remember that in the early universe, photons and baryons were tightly coupled to each other. So there are sound waves propagating throughout the universe in the primordial plasma until recombination happens, where this sound horizon, basically the size of the distance that traveled the sound wave from the Big Bang to recombination, is frozen on the surface of glass scattering. And we can see this, and we observers are sitting at the origin here on the graphic on the top right. And so we are basically seeing this sound horizon frozen in the CMB, and we measure this as an angle in the sky, which is called theta s. And so basically, if we know the physics of the early universe, we can calculate the distance that this sound wave traveled till recombination. And once we measured the angle, which is exquisitely done by Planck, then we can infer the distance at which we observe the CMB. And this is the formula that I'm showing here. So the distance can be expressed in terms of cosmological parameters, where I have factored out the H0, or 100 times H in green here. And so we can play the game and see which combinations of parameters in the dark sector will give us the right distance. And so if I do this, you see on the figure on the left, I'm showing, for instance, you see that on the x-axis, I have the equation of state for the x component. And as I go to phantom and more phantom values, I'm going to raise the value of h that I infer. And when I introduce a negative cosmological constant, this changes because basically the steepness of the relationship between h and w will change, so that I will effectively need less phantomness to achieve higher values of h naught. And this can easily be generalizable for various type of parameters, and this is the relationship that I'm showing here. And so I can go now and compare this to supernovae BAO and this theta S that I measure with Planck. And so I'm showing here various different type of models, and you always see the same model, and beneath it, it has the addition of a negative cosmological constant. And you see that the column that I want to stress here is the blue one, which shows the base factor. This will tell us whether the model is favored or disfavored with respect to the null hypothesis, which is lambda CDM here. And you see that in most cases is disfavored, but for some of them we have a better fit to the data. And now if I add a high value of h naught, then you see that the result don't change that much, but we do get some models that have better fit, and which gives us larger values of h naught. So you see here you see the posteriors, and it's quite shifted to the right, even though it's not sufficient to solve the tension. So my time is done. Here are my conclusions. I'm happy to take questions, and you can text me on Slack. Thank you very much.
Thank you, Rodrigo, for your talk. Is there any question? There is one hand. Pilar, go ahead. No, Pilar, you are mute. Okay.
Yes, sorry. So you mentioned at the beginning some symmetry behind this negative cosmological constant. Can you say what you meant by that?
It's just that from a high energy, if you take high energy physics considerations, so you have for instance, the ADS CFT correspondence, the fact that you have a negative cosmological constant gives you a lot of theoretical background, if you want, that you can exploit, and yeah, it's just this kind of things I was referring to.
Okay. Is it okay, Pilar? Do you have further questions? Okay, fantastic. Okay, so thank you very much, Rodrigo. Let's move to the last. Let's close the student forum. Let's move to the last talk of today. People, remember, please, that after this talk, Seida's talk finishes, we are not done yet. Belen is going to announce the winners of the poster session and do the whole ceremony. So please stay tuned, don't leave. Just bring your coffee to the screen. Okay, so now, Seida, if you are ready, whenever you want.
Yeah,
okay.
Do you see my screen?
We see your screen, we hear you.
Perfect.
We even see you.
Oh, great. Even better. Yeah, thank you very much for inviting me. I wanted to talk about particle oscillations and how they can play a role in explaining the matter-antimatter asymmetry of the universe. And I picked particle oscillations because I assumed many people here are interested in neutrinos, so they are familiar with oscillations already, quantum oscillations already. But let me start with kind of talking about the matter-antimatter asymmetry of the universe. So we can tell that we are made of matter, and pretty much everything we can observe in our universe is made up of matter instead of antimatter. And so our universe has a long history, is 13.7 billion years old right now, but we know that by the time it was about a minute old, or actually tens of seconds old, this asymmetry was set. So even the universe could have started, even if the universe could have started with equal number of particles and antiparticles, by the time that light elements were light nuclei forming, this is the Big Bang nuclear synthesis, there were basically no antiparticles left. Everything was pretty much just matter. So this is basically the timeline that we are setting, and we can quantify this. Sorry, my slides are not progressing. Oh, okay, good. We can quantify this asymmetry. We can actually measure it at two distinct times in the history of our universe. One is, as I said, is at the time of Big Bang nucleosynthesis. This is when the universe was about 10 seconds old. The plot we are seeing on the right shows the abundances of light nuclei in our universe. So y-axis is the abundance. So the first one is the helium-4, deuterium, helium-3, and lithium at the bottom. And the x-axis is the baryon to photon ratio, which is defined here eta. So it is the density of baryons minus the density of antibaryons over the density of photons. So of course, the abundance of an element just depends on the density of available neutrons and protons around, basically. So that's quantifying that. The baryon to photon ratio is quantifying that in a way. The yellow bars on this plot are the observations, and the lines are theoretical predictions. The other period we can measure this asymmetry is from the cosmic microwave background. That is when the universe was about 400,000 years old. So this is like much later than BBN. And that measurement is shown on the plot as a CMB bar. So you can see that, especially if you look at the deuterium measurements, for example, and also helium, it agrees very well with the cosmic microwave background measurements. There's a lithium problem, but we won't go into that. So overall, so we know now we quantified the asymmetry. We know that there's more matter than antimatter, and how much more is this ratio, baryon to photon ratio eta? It is about 6 times 10 to the minus 10. So this is the experimental result or the observation. What does this mean for a I don't know. Oh, I see. I need to click on it. What does this mean for a theorist? So this means okay, this is a very, very rough estimate, but this means that in the early universe, or at least by the time that BBN was happening, there needs to be one extra quark for every about 10 billion quark-antiquark pairs. So, and how can that be from a theoretical perspective? Well, the rules that a model, a physics model or a particle physics model needs to satisfy to generate such an asymmetry was set by Sakharov in the 60s. And there are 3 conditions that must be satisfied. One of them, the first one is that baryon number or some matter number cannot be a conserved quantity. So you need to violate baryon number. This is kind of obvious. You need to violate baryon number to produce an asymmetry. The second condition is that charge and charge parity asymmetries must be violated. Charge parity is just a way to distinguish between a left-handed particle and a right-handed antiparticle. So if there's an asymmetry, that means that your physics model is differentiating between a particle and an antiparticle. So CP must be violated as well. And the third condition is that there must be some out of equilibrium process, preferably a process that is violating both baryon number and CP asymmetries needs to be out of equilibrium. And this is because in thermal equilibrium, any process that happens one way happens at the same rate in the opposite direction. So if you are producing baryon number, for example, you might as well just be washing it out. So if they cancel out in a way in thermal equilibrium. So your process needs to be out of thermal equilibrium. Of course, when you have the rules, the first thing we can ask is if the standard model satisfies these rules, because standard model is otherwise a very good theory. So the first Sakharov condition, baryon number violation, is actually satisfied very well in the standard model. Weak interactions, this process is called sphalerons in weak interactions, and they violate B plus L, so baryon plus lepton number is anomalously violated. And these processes are very active at high temperatures, above the electroweak scale, and the sphalerons in their thermal rate is goes like about alpha weak to the 5T to the 4. So this is This is actually very, very efficient. But at low temperatures, after the electroweak symmetry is broken, that after the double gauge bosons get mass, basically, this rate is suppressed exponentially by e to the minus mw over alpha weak times t. So this is, this suppression means that right now at 0 temperature, our universe is no more violating baryon number. So we are stuck with the baryon number we have with the standard model. But at the very early universe, standard model could have been violating baryon number. The second condition, CP violation, also exists in the standard model. We know that the CKM matrix, which describes how quarks mix with each other, has a phase which is CP violating, which means it's CP violating, and we measure the CP violation as well. And it's too small. We actually, we can measure it. However, in order to produce the baryon asymmetry, how the CP phase gets into the calculations is a bit convoluted, and we can estimate it as we can estimate the baryon asymmetry you would have gotten from the CP phase, and that's about 10 to the minus 20 or so. So even though the CP phase is there and maybe not too small, but the baryon asymmetry it can produce is 10 orders of magnitude smaller than what we observe. And the third condition, the need for an out of equilibrium process, is not satisfied in the standard model. So all of the standard model processes are in equilibrium before BBN. Some of them become out of equilibrium much later, but they are in equilibrium by the time of BBN. And the only possibility was for Higgs to be a light particle, which would have given us a first order phase transition, electroweak phase transition. But we know that Higgs is heavy, so there is no first order phase transition in the standard model. So this is the standard model. So this means that we basically need new physics to explain the baryon asymmetry of the universe. And we know that this new physics need to couple to the standard model because you need to produce our baryons, and it needs some extra CP violation and an out of equilibrium process. This is, of course, if you are using the Calderons to satisfy the baryon number violation condition, but you can also add a new process to violate the baryon number as well to your new physics. So this is what we need, and of course there are a lot of new physics models to explain the baryon asymmetry. This is just a very rough categorization of those models. So please don't take this as a complete summary. So there are kinds of models which add just extra scalar fields, like the Twix-Albert model, MSSM, and MSSM, what have you. This, if you add a new scalar to the standard model, you can get a first order phase transition pretty easily, and also you can have CP violation in this new scalar sector. There are also types of models that actually don't use well, let me not say that. There are types of models which rely on out of equilibrium decays of some of new particles. This is, for example, leptogenesis is a good example of this. And in these out of equilibrium decays, you can get CP violation between three-level processes and between three-level decays and mid-loop processes. And you can also say there's this other problem with the standard model, dark matter. We don't know what it is, and there can be a dark sector, and maybe there's an asymmetry in the dark sector, which is then translated into the visible sector to our sector, basically. So this is an asymmetric dark matter. An asymmetric dark matter scenario can also give rise to a standard model asymmetry. So these were the kind of the older new physics. But before going into the new physics model that I will talk about from particle oscillations, I want to revisit the standard model CP violation just briefly, because it will be relevant for our new physics model setting. So in the standard model, we observed CP violation, as I said, and we observed it in mainly meson systems, neutral meson systems. These are kaons, B mesons, and D mesons. A very interesting property of these mesons is that they oscillate. They oscillate between particle and antiparticle or meson and antimeson states. And I want to say that CP violation in the meson systems weren't only from oscillations. The observed CP violation weren't only from oscillations, but oscillations themselves are very interesting. The reason they oscillate is that their mass eigenstates and interaction eigenstates are not aligned. For example, here's a diagram for kaons. So there's a box diagram between this k and k bar coming from weak interactions. And if we write the Hamiltonian of the system, there's a mass matrix and there's an interaction matrix gamma. Excuse me, interaction matrix gamma. And this is of course, after producing kaons, they propagate, and the propagation is governed by the Hamiltonian. And if you find the eigenstates of this Hamiltonian, you will find a heavy and light eigenstate, which are the two orthogonal sorry, it's too early here. Which are a mixture of B and B bar states, basically, or K and K bar, or D and D bar. So this fact that we measure the mesons via their interaction, so we measure their B and B bar, but they propagate via their, of course, Hamiltonian, the eigenstates of the Hamiltonian. This gives us the meson anti-meson oscillations. It's a nice quantum mechanical process. So similar, and these oscillations. So this is just a picture of some oscillations, nothing to do with the actual B meson or the kaon system. So these oscillations, there's a very important parameter that for these oscillations, that's x. X is the ratio between the mass difference between the heavy and light eigenstates, delta m, over the decay width of the particles, gamma. So the delta m itself actually tells you the frequency of the oscillations. So you see here the frequency of the oscillations. Here, let's say the orange line is a meson and the blue line is an anti-meson, or vice versa. So if you start with here, I'm setting up the system to start fully as an anti-meson system, but then as it decays, it starts also oscillating, and then you produce mesons later as well, but then the mesons turning into antimesons, and that oscillation continues. The frequency is governed by, as I said, the mass difference, and we know this from neutrinos as well. And of course, you have an exponential decay envelope, which is 1 over gamma. So if this x parameter is about 1, you get some nice oscillations before all of your mesons and antimesons decay. So x around 1 is a very nice, very nice spot. If x is too large, the oscillations are too fast, so they kind of gets washed out. And if the x is too slow, well, you don't get to oscillate before all of the particles decay. So this is the sweet spot. X equals 1 is the sweet spot of oscillations, which will come back again. So taking these oscillations as a backdrop for explaining the matter and antimatter symmetry, my collaborator John Marsh Russell and we looked at a generic new physics model. So instead of a scalar particle like mesons, we actually looked at a fermion, a Dirac fermion with an approximately broken global U1R charge. So for such a Dirac fermion, you can write this mass Lagrangian. Here, capital M is a Dirac mass, and the small m is the Majorana mass. So I'm saying Dirac actually, but this particle is actually a pseudo Dirac fermion in this case, because U1 is broken with the Majorana mass. And let's add interactions for this fermion. Here is psi and psi c. Psi c is, of course, the complex conjugate of the fermion, with some operator here, OB, which this operator carries baryon number +1. So, for example, this can be a UDD operator. So this is the only Lagrangian, or the new physics Lagrangian. And if we look at this, what this Dirac fermion does in the early universe, it follows a Boltzmann equation, like the one that we saw a couple of talks ago. So here, Y is the density matrix, is the psi c for psi and psi c. H is the capital H is the Hamiltonian, and there's another H, of course, is the Hubble parameter. And this fermion is, of course, interacting with other stuff through the operator OB, and these interactions are, can be scatterings or annihilations. And here, plus and minus, the O plus and O minus are the diagonal matrix, either 1, 1 or 1 minus 1, depending on the nature of the interactions. And these interactions can be of two types. One of them is called flavor blind, and the other one is flavor sensitive. This is flavor. I'm saying flavor, but the flavor here is the fermion and antifermion, or particle and antiparticle. So if the Lagrangian can't tell the difference between a particle and antiparticle, like a scalar interaction, you call this flavor blind interactions. And if it can tell this tell the difference between a particle and antiparticle, is called flavor sensitive interactions. An example is vector interactions. So, the interactions, of course, are given by whatever model you pick. So it's not you can set up your model to be either flavor sensitive or flavor blind in a way. So early universe is very complicated. These particles, after being produced with everything else, are in a hot and dense plasma in the early universe. So that, of course, affects their interactions. And at the same time, the universe is also expanding. All of this information is in the Boltzmann equations, of course. But here I'm just showing as an example, what kind of rates that how those different processes differ from each other between their rates. So blue is the Hubble rate. You see an annihilation rate with a cross section of one femtobarn. Actually, the annihilation just comes from of course, the interaction terms that you put in, and the same interaction terms also give you an elastic scattering rate. So and after this, of course, at the end, you also need to produce a Bayesian symmetry. And this is, again, just an example process, and I will give you more details. But in this example process, the particle is 300 GeV. The particle mass is 300 GeV, and the decay rate is about 10 to the minus 6 EV, with an oscillation frequency of 10 to the minus 5 EV. So, or the mass difference between the heavy and light particles are 10 to the minus 5 EV. So usually, if there wasn't any interactions, these particles actually would start oscillating just when the oscillation frequency or the Hubble rate drops below the oscillation frequency, so about z equals 5 or so, or 4 or so. However, since there are interactions, particles cannot start oscillating because the interactions just keep them in the particle and antiparticle state they have, and either the annihilations or the elastic scattering. So the annihilations here actually freeze out pretty fast because they get Boltzmann suppressed pretty quickly. So the governing interactions here are the elastic scatterings between these new fermions and the standard model particles, and those only become smaller than the oscillation frequency about z equals 50. So in this scenario, actually, the particles cannot start oscillating until the temperature dropped below the 60th of their mass. So they actually need to wait quite a bit. And after they start oscillating, they're of course decaying as well. And those decays will produce produce baryons. And if there's CP violation in the system, they will produce a Bayesian symmetry. So on top of the Boltzmann equation I showed you, you actually need to add 2 more equations to find the Bayesian asymmetry, but approximately that asymmetry, the Bayesian asymmetry, can be found via this equation here in the purple frame. So your epsilon is a measure of CP violation. It is the difference between the probability of a psi particle decaying into baryons and a psi bar particle or psi c antiparticle decaying into antibaryons. So is measuring that quantity, and gamma is of course the decay rate, and sigma here is the total density of both psi plus psi c particles. So the leftover particles psi and psi c, the ones that haven't decayed, they will be oscillating and then decaying, and if there's CP violation, epsilon CP violation in the system, those will end up producing a Bayesian asymmetry. So this is the process that that we want basically, and all right. And you can actually solve this. This is very nice. You can actually solve these by the Boltzmann equations via some assumptions or simplifying assumptions just with pen and paper, and they give you a pretty good answer. But you can also just solve them numerically, which is better. So here are the results for a set of parameters. So again, the mass of the Dirac fermions or pseudo-Dirac fermions are set to 300 GeV. The mass difference is about 2 times 10 to the minus 6 EV. The decay rate of 10 to the minus 6 EV. Phi gamma is the CP phase in the oscillation Hamiltonian. So what you're seeing here are 3 different abundances. So first of all, the total density of the psi and psi c psi particle, the fermions and antifermions. So that's sigma. And of course, you start with a thermal density, and then of course they are decaying. So you see the exponential decay as well. And you see 2 different lines, dashed and dotted. One of the dashed is for interaction strength of 1 attobarn, and the dotted is 10 to the minus 2 attobarn. So it's much smaller. The delta Z is the fermion-antifermion asymmetry. So this is not the baryon asymmetry, but the asymmetry between fermions and antifermions, the psi and psi c. That asymmetry, you are producing a fermion asymmetry as well because of CP violation, but of course all your particles are decaying, so that's why that asymmetry is decaying. And as those particles decay, the new fermions decay, they are decaying into baryons, producing a baryon asymmetry. So the asymmetry in the delta kind of gets translated into the asymmetry in the baryons as well. And at the end, what we end up is just baryons, but more baryons than antibaryons specifically. So this delta B is the baryon asymmetry. And the solid bar is the observed asymmetry. So you want to you want to of course explain this. Here we are producing more baryons than needed, but this is just to give ourselves enough playing room basically. And these results are for a flavor sensitive interactions, flavor blind interactions. They're easier to produce the asymmetry actually with them. So this is nice. So this is just showing you with a generic scenario, you can get this asymmetry. And I also wanted to show you the Goldilocks principle in play. Basically, what you're seeing here is again the baryon asymmetry on the y-axis, delta B, and the mass difference between the heavy and light eigenstates of the fermions and the x-axis for different gamma, for different decay rates. You can see the baryon asymmetry is largest when gamma is about m basically. So you can see this like nice optimization around gamma equals delta m, which is which corresponds to x equals 1 for oscillations. And these the 2 different curves are one of them is for flavor blind oscillations and one of them is for flavor sensitive oscillations. And so I don't have much time, but I want to say that this was a generic scenario, but we also looked at a specific new physics model, which was a pseudo-Dirac Bino in a U1R symmetric MSSM model. And this had, we also added, of course, R-pair violating interactions to get the baryon number violating decays. And for that scenario, of course, you are more constrained because it's an MSSM scenario, so you have certain interactions that you need to add and stuff. But you could get the correct baryon asymmetry, which was nice. And later, actually unrelated to the baryon asymmetry, my collaborators and I, we used a similar pseudo-Dirac Bino in a U1R symmetric SUSY model to explain the neutrino masses as well, which was, as I said, separate, but maybe we can combine the 2 scenarios, which a pseudo-Dirac Bino which explains both neutrino masses and the baryon asymmetry. So it will be like a pseudo-Dirac leptogenesis scenario, but we haven't done that yet. It's a bit harder than the one that I talked about. So and I'm not going to go into the details of the model. You can look at my slides. And I wanted to end with remembering my advisor, Anne Nelson, who loved working on baryogenesis. And she also have models using particle oscillations to explain the material symmetry. And here are just 2 examples. And I miss her. Thank you very much.
Thank you, Seida, for the talk. I think we all remember Nelson kindly. And is there any question? Yes, Thomas, please unmute and go ahead.
Yeah, thank you. I have a question. I mean, there is this scenario sometimes called ARS leptogenesis, where you have two heavy sterile neutrino, which also oscillates. This seems very similar to your scenario. Can you tell me a bit the difference between the?
Yeah. No, it is very similar. I should have put a slide on that as well. So in that scenario, those are flavor oscillations, of course, which is not that different in terms of the mathematics that goes. And I think in that scenario, how you get a resonance is it's like you need to the states need to be very similar to each other in terms of mass. Like the mass difference needs to be very small, and that's how you get a resonance. Basically, here the mass difference can be large as long as it compares to the decay width. So I think that's the only difference I can think of. But that's a very nice scenario.
Sorry,
as well.
But you had your gamma. Is this? That's the your lowercase m. No, this your little m is the mass difference, right?
Yeah.
So which is also very degenerate. No, if you have 300 GeV and
it's very degenerate, but I mean, you can tell it can be a bit larger as well. That's true. But the let me say, the thing is, it could have been larger, I guess. It's just that gamma needs to be small in a way, like can't be too large because you want it to decay out of equilibrium. So does that make sense? Like theoretically, both could have been larger, and you could have still gotten some CP relation. It just wouldn't have been enough time to to explain the explain the Bayesian symmetry.
Okay.
Pilar?
Just a comment about this point. I think, I mean, in ARS leptogenesis, you don't need necessarily very degenerate neutrinos, okay? There are regions of parameter space where this is not necessary. Again, also in that case, there is this same effect, of course, that you get the maximum when gamma and delta m are similar. But this is a very generic feature of oscillation behavior. No, I just had a question about, you mentioned flavor versus non-flavor, and I didn't quite get what flavor means in this model. I don't know if you have a complete model with a full standard model, or what do you mean by flavor here?
The flavor, sorry for the calling it flavor, is just the difference between psi and psi c, the particle and antiparticle. So, when you take a particle to an antiparticle, is your Lagrangian going to itself or minus itself? That's the interaction term. So, for example, an example is scalar interactions. If I take psi to psi bar, they just stay the same. They're flavor blind. But for vector, you just reverse the sign basically, and that's flavor sensitive. That's called flavor sensitive. And for example, for a Bino, you have vector interactions. So that would be a model with flavor sensitive interactions. And flavor is, again, it's just a particle or antiparticle.
So this is the kind of interactions that you have included.
Yeah. So a more specific model is, for example, this. So the upper part is basically, so this is that R parity, R parity violating interactions, for example.
Okay, thanks.
Yeah.
Okay, if there are no further questions, we close this section, but people, please don't leave, because Belen is now going to do the award of the poster prize.
Okay, so I go ahead, right, Gabriela? Okay, so hello to everybody. Here we are for the poster competition. I want to warn you of the following, or to make a comment that I often made when in previous occasions, which is that you will see the posters most voted are great, but for the participants, this is this is a game, not a joke, but a game. What I mean is that do not think because if yours does not appear is necessarily worse or anything like that. If there is some unfair competition, is this one in which all type of sociological things play. And in particular this year, if you realize, I mean, we hesitated in doing it because getting to the poster, if you really want to watch all the posters, you have to go click and click and click one by one. While in a normal conference, you just walk around the room, it catches your eye, it's different, right? So this is just to, not to diminish what came out, but to have this very much in mind. Okay, anyway, it was very, very dispersed. And here is, let me share the screen, share screen. You see this, right? You see my screen? Gabriela?
Yes, Belen, we see.
Yes, I'm sorry, I see your screen, but I was muted.
Okay. So here are the results of the poster competition. We are going to give, I mean, we are showing the 3 most voted in alphabetic order. They were very tight, but in any case, if they go in alphabetic order, okay, taking even more seriously doesn't seem, I mean, the ordering doesn't seem serious in this case. So in alphabetic order, one of the 3 awards goes to, goes to Hannah Banks from the University of Cambridge. Please, Hannah, are you around there? Let me see if she's there. She's not there?
She's not.
Okay, she's not there, so then she cannot say hello, but we will congratulate everybody at the end. And this is the poster. Wow. Okay, so I stop sharing if I can. Okay. Do you see this? Okay. No, of course. Don't worry. I go back to this share. And maybe I don't put them. I don't know why there is this problem right now. So the first one is Hannah Banks. And here is the poster. I try once more to make it play. There, good. It's charting the 5th landscape. Okay, that is one. Now, next one is Ana Luisa Fogel from the University of Sao Paulo in Brazil, for a poster on supernova for coherent scattering, supernova neutrino detection via coherent scattering of silicon nuclei. You can check it. And the third one, I mean third alphabetic order, goes to Stefan Sandner from the University of Valencia in IFIC for a poster on how to relax the cosmological neutrino mass bounds if the neutrinos are unstable. Okay, so I am, okay, these are the 3 of them. Are you there, the other 2?
I'm around here.
That's okay. So you see Stefan.
Hello, I'm here also. Thanks a lot.
So congratulations. You are going to receive, the 3 of you, a small present from us, a cup and something else. Okay.
Nice. Thank you.
So thank you very much to you and all the others for participating. I think that some nice features of the final things is that it is for me, geographically balanced. We don't want to be closed on Europe, so there is one from Brazil. Is also not just node members, because University of Cambridge is not a node, so that is good. We like to be open. And of course, it is a gender balance, which is also nice. Okay, so you can look at the 3 of them there, Hannah Banks, Ana Luisa Fogel in the list, and Stefan Sandner also there. Okay, so thank you very much to everybody. Congratulations to these 3, and we can rest and meet back at 5 on the dot for the. Let me unshare. Okay, so let's meet again at 5 p.m. 5 p.m. Yes, for the final session, which has only 2 talks. Okay, so. Good rest now, and congratulations again. Okay.